Okay, we're going to be discussing what's called integration by parts. And so integration by parts is necessary when you have kind of a difficult integral to work with. And what you need to do is you take a look at the integral and you have to pluck out a function and a derivative. So in this case, that's where I'm saying u, and we'll call that our function, and then dv our derivative. We have to be able to take the integral apart. And once we write and figure out what u and dv are, we can write it as uv minus the integral of v du. Okay? Now that sounds really complicated, and it probably is more complicated than it actually is. What we need to remember is this kind of rule here that says I late. And so what I'm going to do is I'm going to highlight this here for you. I late. This is kind of the order of precedence in which you should pick what it is that you need to integrate. And we'll see this in practice when we look at an example in just a minute. But this right here represents the decreasing order of difficulty in carrying out an integration. So you need to be able to pick out, well, what's my u and what's my dv, in other words. And so it says, for example, inverse trig functions are the most difficult to integrate, while exponential functions are the easiest. Thus, we should choose the first function in this order. So the lower it is, the more likely it is we need to integrate it. Well, there is a trick to doing this, and you can integrate by parts using a table. And there was a really famous movie about a math teacher, and in the movie he starts talking about to his students about tic-tac-toe. All right, and he's actually doing integration by parts. If I can find the movie clip, I'll go ahead and put it in the description, and it might be a movie worth watching. So what we're going to do is we're going to examine this right here, and we're going to notice that we look at the integral of u dv, which is right here, and I want you to notice that for u, they take the derivative, and for dv, they actually integrate. Okay, so we're going to kind of keep this in mind, and I think you'll see that it's a lot easier. Okay, so I'm going to first do this in the traditional sense, that we're going to integrate using integration by parts, the formula here given on number 2 or number 1. It's the same thing. And then we'll use this tabular method, and then you can see and compare. All right, so let's take a look at an example. Let's suppose that I have 7x sine x dx. Okay, so I'm going to figure out, well, what is it that I want to integrate? What is it that I want to take the derivative of? All right, in this case, they're probably about equal in terms of integrating and taking the derivative. So what I'm going to do is I'm just going to say, okay, well, this 7x will represent my u, and my dv will represent this sine of x. Okay, so let's see. If I do that, if I say u equals 7x, and if I say dv equals sine x dx, okay, well, I can easily find my du. That is just 7. Okay, but if I integrate sine to get what? Well, when I integrate sine, I get negative the cosine, if you remember. So now all I have to do is say, okay, then there's nothing difficult about this. My integration by parts formula is telling me u times v, so 7x times negative the cosine. Okay, so let's just say negative 7x and then cosine x. All right, there we go. Negative 7x cosine x minus, and then it's going to be the integral of v du. Well, v was negative the cosine, so another negative cosine of x, and then dx. Okay, so this becomes plus. And so what do we get? We get a negative 7x, and then the integral of cosine is, of course, going to be sine. Okay, there we go. And so, okay, I'm sorry. I got sidetracked a little bit. I forgot to write this. Negative 7x cosine of x. That's from the first part. plus, and the integral of cosine, of course, is sine. There we go. That looks a lot better. Plus your constant of integration, c. And actually, what am I forgetting? Okay, it should say v du. All right, it should say v du. So let's go back and just fix that really quickly. My apologies for forgetting that. All right, so we should have a 7 here. We should have a 7 there. So it should be a 7 sine of x plus c. Okay, so this right here is my integral. All right, and let's go ahead and use our tic-tac-toe kind of method. So here's what we need to do. We're going to have a plus and a minus, and it's going to alternate in sign if we have to take successive derivatives. But what I'm going to get at is that you're going to want to take the derivative up until you can get 0. All right, up until you can get 0. So I'm going to write this in a different color, plus and minus. So we're going to start off with our u in this case, and our u we said was 7x. Okay, and then we're going to start with our dv, in this case was sine. So what we're going to do is we're going to take the derivative here and we're going to integrate here. All right, so let's take a look and see what we get. Well, the derivative of 7x is 7. All right, and I'm going to take the derivative one more time and I'm going to get 0. So plus, minus, and then I'm going to need to write then plus here. All right, now I'm going to take my sine, okay, and when I take the derivative then of sine, the integral of sine, I'm going to get negative the cosine, okay, and then I need to take it one more time because I have to satisfy that last row where I wrote 0. So if I integrate the negative the cosine, well, the integral of cosine is sine, so I'm going to get negative the sine in this case, and it looks just like that. Okay, so now what I do is I kind of put a ring around what I have here, and this is the way that it works. Just like that, and then I kind of put it all together. So what does it look like? Negative 7x cosine of x, and then it's a minus times a minus, negative 7 times a negative 7 negative sine of x. So that becomes plus 7 sine x plus c, which is actually the same conclusion from the very last problem. Okay, so again, really there's nothing to it, but we can go ahead and take a look at one more example. Okay, so we're going to take a look at a few more examples. So here is the next example that I'm going to look at. It says 2x e to the x dx. So I'm going to exclusively use that chart, that table that I just talked about. So let's go ahead and write it out here. All right, I'm going to put plus and minus, and I'm going to want to take the derivative of 2x. So that means I'm going to want to integrate e to the x, and that's actually a good one to integrate. So let's take a look. If I take the derivative of 2x, I get 2, so I'm going to have to take it one more time so that I can get 0. So I need to write a plus here, plus minus plus, and it follows that pattern if you have to keep going. All right, when you integrate e to the x, you get itself e to the x, and so you integrate it one more time, you're going to get, again, e to the x. All right, so really there's nothing more to this, okay? If you follow the pattern that we set up in the last example, this right here corresponds to the actual integral. Again, do not forget the constant of integration. So we have 2x e to the x minus 2 e to the x plus c. And this right here is our integration by parts done. All right, let's take a look at another example. Call this one number 3. And let's say this is e to the 2x x squared dx. Okay, so in the last example I failed to note that this was u and this was dv right here, but I'm going to tell you now how to do this. On number 3 here, let's say that this right here, x squared, is going to represent my u. So I'm going to write that as u, and my e to the 2x will represent my dv. Now the reason for that is because x squared is one of those easy ones to take the derivative of, so that eventually you'll get 0. All right. And so again, it's following that I late, okay, where we want to integrate the exponential function. All right, that makes it a lot easier to do. So let's see here. Looking at my chart, all right, I'm going to do plus and minus, and let's see what I've got. In the first case, I've got my x squared, and in the second case, I've got my e to the 2x. So let's say the derivative of x squared is 2x, so I'm going to have to keep going. Derivative of 2x is 2, so yet keep going just one more time, and then I end up with my 0. So plus minus plus minus, and now let's see here, if I have e to the 2x and I want to integrate that, that's not a big deal. All right, you're going to get itself e to the 2x, all right? But you've got to account for the derivative of the 2x, which is 2. So by consequence, what would you need on the outside? If you can write a 2 in there, well, by consequence, you're going to need a 1/2. Okay, and that will take care of that business. Well, you're going to want to integrate it yet again, because you need to actually integrate it a couple more times. So it is partially its own integral, but then you have to account for that derivative of 2x, which is 2. So again, by consequence, you need another 1/2. So this actually 1/2 becomes 1/4. Okay. And you should kind of start seeing the pattern. Well, it's again going to be partially its own integral. 1/4 in this case is still there, but you need to account again for that 2. Derivative of that is 2, of 2x is 2, so you're going to need by consequence a 1/2 again on the outside. So 1/4 times 1/2 being 1/8. I hope that makes some sense there. All right. And so now we've got enough information to proceed with our integration by parts. And we're going to follow this little pattern here. All right. And it's laid out very nicely. Okay, so this one's actually longer. So if you were to actually do the integration by parts, it would be significantly longer. So in the first case, we're going to have 1/2, all right, of x squared e to the 2x. That's a given. And then negative or minus the 2x times the 1/4 actually creates a scenario of 1/2 of x e to the 2x. And then plus, okay, so it's again alternating sign there. 2 times 1/8 is 1/4, so 1/4 of e to the 2x. And then plus c, your constant of integration. All right, and then we'll take a look at one last example here. Okay, so let's take a look at another example here. We have x squared times the natural log of 3x dx. And what I'm going to do, I'm not actually going to use the table here so much as that I'm going to use what I had started off with. And so that is, I'm going to label this one to be u. All right, because this one will be easier to take for me to take the integral. And this one right here will be my dv. That one will be easier to integrate. Again, I'm not going to use the table. I'm going to use this main idea that we started with, which was the integration by parts. I'm going to say u equals the natural log of 3x. And in that case, my dv is my x squared. So du is the derivative of the natural log of 3x, which is 1 over 3x times the derivative of the inside, which is 3. So the 3's cross out, leaving me with 1 over x. And my x squared here is pretty straightforward. All right, it's x cubed over 3. Remember, you add 1 and divide by the new exponent. All right, so now we're going to use our fact that uv, the integration by parts formula, is going to be x cubed over 3 times the natural log of 3x. Okay, so there's my uv minus v du. So what I'm going to do is minus the integral rather of v du, which is x cubed over 3 times 1 over x. All right, and then there's your dx. You can't forget that. So let me write that in there for you. All right,
And so you have something that's really quite simple. You end up with the following. The first part we don't touch. It was already integrated for us. All right, based on the formula here. But the second part you do integrate, and you can actually power reduce x cubed over x becomes x squared. So you basically have 1/3 of the integral of x squared. So x squared over 3 in other words. And that's pretty easy to integrate at this point. Okay, so what does it look like? Our final integral, x cubed times the natural log of 3x minus, and so x squared over 3 becomes x cubed over 3 times 1 over 3. So x cubed over 3 times 1 over 3 plus c. Not terribly difficult here then. It's just this right here. X cubed over 3 times the natural log of 3x. Let's see here. Minus x cubed over 9 plus c, your constant of integration. All right, nothing really to it. Again, this one not really necessary to use the table, but whenever you have a function that you can take the derivative of, and get 0, you can use the table. Other times just stick with the integration by parts formula. But these right here are some solid examples that you can definitely use in practice in doing the integration by parts. So as always, I hope this video was helpful, and remember, like and subscribe.